Hello, my name's Kai. I'm here to talk to you today about orchestration frameworks, and we're going to take a look at three of the main ones. They're by no means the only ones, but they're probably the most recognizable ones. I do some work for Cluster HQ, doing a bit of work for JetStack. I'm kind of generally around in Bristol. I've spent the last year working very heavily with these three tools. I probably know very little about them, so excuse me if I misinform you for the whole day, but I'll tell you what I know and we'll see where we go with that. So, what's orchestration? Let's start there. This is Thomas Beecham. He's a conductor. He's fairly well known in the world of conducting. His job is to take like a rabble of people who turn up late and often argue with each other and try to turn what was a beautiful composition, like the desired state in some genius like Beethoven's mind, he has to turn that into reality somehow, right? Now, if you're composing something, you get this wonderful kind of hassle-free practicalities don't matter. You're thinking about the music. This is the developer. You're thinking about what should actually happen. To actually make an orchestra sit down is no easy task, right? You have to coordinate them, get the timing, tell them to shut up, like, no, you're completely out of time. It's a difficult task. So the metaphor for orchestration is, in a computing sense, how the hell do we throw loads of different workloads at thousands of computers, get them all to sit in the right chair and behave? This is effectively what the kind of overarching umbrella title of orchestration is. It's not a single thing. It's basically, I want to throw a load of work at a data center and I want something to make sure that that runs at scale and dealing with failures and that kind of thing. So there's kind of a bunch of different sections. We're going to go through a kind of, what are these sections, what do they mean, and then take a look at the different frameworks. So scheduling, this is probably the core of an orchestration framework. It's like, I need to put some stuff in the right place at the right time. Let's say we have, a small cluster of 100 computers, and we have a whole bunch of different workloads, some of which are big fat database servers, huge data processing processes, others are very small little worker processes. How do you work out which computer to put which job on at the correct time? And it sounds quite simple if you only have a couple of computers and a couple of jobs to throw at those computers, but it soon gets pretty complicated pretty quickly. Like, this machine is 50% full, so we have capacity on that machine. We could throw something on that machine. But it only has 4 gigs of RAM, and the thing I'm trying to throw onto it is 6 gigs, so obviously we can't use that machine. Now, if we start to talk about hundreds of microservices and thousands of computers, I mean, life's too short. I don't want to do that job. So the main job of an orchestration framework is to schedule a job, as in a process, onto the correct machine for the time. It can get pretty complicated, like this board. And I really like to ask the man in the blue. I'm like, who is this guy? He's like the god of scheduling or something. Right, scaling. This is another part. Like, it's not much point in kind of thinking about running stuff in large-scale data centers if you can't increase capacity or remove it to save money if it's a Sunday afternoon. So these frameworks, they need to be able to incorporate new capacity. You need to be able to add new capacity and remove it. Amazon auto-scaling groups is a good example of a kind of scaling side of an orchestration framework. You need to be able to add capacity as the load grows. Monitoring, like, you need to know if everything is working, right? So how do you know that? Well, you put health checks in and you check that services are working, you're checking that machines are working, and you need to react to these events if they go wrong. So if a machine goes down, let's use the scaling feature that we talked about just now and add some more capacity. If a process goes down but there's nothing wrong with the machine, then we'd probably want to give it a kick and restart it. How do you know about these things? Well, this is another part of an orchestration framework is, keeping a tab on what's actually going on and knowing if a failure has happened and maybe knowing if everything is working. This is a nice side of monitoring. Like, hey, thumbs up, you can go to bed. We want to see all the green ticks across the board. So monitoring is an important part of it. Otherwise, how do you know where you stand, right? Failover. So, like, stuff goes wrong and everything goes wrong at times. But the more that you scale, the more likely it's to go wrong, right? So, hey, I've got one computer, it could go wrong at some point in the next 10 years. 1,000 computers now, it's 1,000 times more likely for that to happen. I actually advocate using gaffer tape. It's really great. Like, it really works in all situations. I'm not sure if that's a spare tire, though. So I just thought, oh, it uses gaffer tape. We'll use that picture. You need to be able to recover from failures is the real point I'm making. So whether it's a node failure, and this ties in with monitoring, right? How do we know that it's failed? Well, this is how do I react to the fact that it's failed? And it's either standing new machines up or it's rescheduling processes that were working on one machine and now they don't, restart them on any of the healthy machines that remain. So you need to be able to detect failures and start processes and machines to replace those failures. Storage, we remember these, I hope. I'm not that old. We need to be able to think about storage because if you don't, then we're in the land of 12-factor apps. Now, show of hands, everybody's comfortable with 12-factor apps? I mean, I'd be shocked if it's 3 hands. Come on, like, I like this game. Let's have our hands up. No, really? Okay. In which case, you've just condemned yourself to an explanation of 12-factor apps. It's basically, in my head, how Heroku want you to write your applications because they don't really think about state, right? They say, hey, throw all your stateless work here, connect to databases that live off of Heroku, like all the Heroku database service. But really, in the modern world of cluster management and orchestration frameworks, it would be great if we could actually have some storage in the same environment in which we're running our stateless apps, and then we could throw the entire stack at one single system. It seems a bit nonsensical to have all of these wonderful orchestration frameworks and yet have to keep the stateful things out of those systems. I mean, again, that's the 12-factor way of doing things, but maybe it's not the best way. So I'm going to encourage the idea that orchestration frameworks need to deal with storage. They need to say, throw your workload at the framework. That could include a MySQL server or a Mongo server or any number of stateful things. And the orchestration framework needs to be able to present storage to where the process ends up. So if we think about scheduling, and I'm throwing a whole bunch of work at the scheduler, and it says, well, I'm going to stick your MySQL on server 3, well, it's pretty pointless if the disk that you had written your data to before that happened is still on server 2. So you need to have something in this orchestration framework that understands that and can move storage around the cluster. We'll kind of get onto that a bit more because Cluster HQ makes a tool that deals with storage, so it's something close to me. Networking. I've never had to deal with this, thankfully, but I'm sure many cabinets have ended up in that state. Really, the main point is that if you have lots of different services making up a microservice stack or however your thing is architected, it's not an opinion, they have to talk to each other somehow. If everything is always in the same place, right, it's fairly simple. You could just hard code the IP addresses and, hey, I don't need to think about it. But then you're kind of limited in 2 ways. First, what if the thing fails? So back to monitoring and failover. Something breaks and moves. Now you have to go and update your code to point to the new place. Well, that's patently not a very good way to do things. Equally, what if we run more than one copy of the service you're trying to speak to, which is more than likely in this world of scaling things. And if I have 10 copies of my news service, I want to hit one of those 10 copies, and I don't really want to think about where they are. So when I say networking, I don't mean RJ45 cables. I mean service discovery and routing to one of the healthy services. And in microservices, that's really important because, let's face it, what is microservices is take one massive process, split it up into other processes. Well, now, how do they communicate? They don't invoke functions in the same process. They reach out over the network. So this is a really important part of this whole world, is how do you actually make that work? And these tools help you do that. The orchestration frameworks have networking features that enable you to do service discovery and auto-routing. And tied up with talking about failover, if something goes down, all of a sudden you've only got 9 of those news services, and the networking layer won't route traffic to the unhealthy one. So it's constantly updating its knowledge of what's running on the network and allowing you to communicate over the network to your services. How do we do all this stuff? this is me in the morning, like how do I go through my day? But it's harder when you have to solve all these problems. And I mean, well, a while ago, 5 years ago or so, there wasn't a clear solution to these problems in one single framework. Things like Cloud Foundry, the early sort of the pre-container solutions existed then, but these days, thankfully, we have a huge number of solutions. Well, a huge number. We have a decent number of solutions, but they all use this same concept. It's like, as a human, we're kind of pretty stupid compared to computers. Well, not stupid, but we're slow compared to computers, right? We have 1,000 computers in our data center, and we have a whole bunch of work to schedule onto those computers. It's going to take a while for a human to sit and think about where am I running the thing on those 1,000 computers. I mean, the whole point of the abstraction of orchestration frameworks is to present you, the developer, or the DevOps guy, the modern cool term for the same thing. Just imagine you have one huge laptop, right, with 1,000 cores and terabytes of RAM. And now you don't have to worry about which computer am I running this thing on. You're just saying, hey, I'm going to develop on my local machine just like I already have. And it's an abstraction. It's not an actual computer with thousands of cores and loads of RAM, although, hey, soon we may get there. It's the idea that you just tell a thing what you want to do, as though you were telling one machine what processes you wanted to run. And behind that abstraction, the thing will look after where on the cluster of 1,000 machines it will actually run each process. So it's a really useful abstraction because it means you don't have to worry about where everything is running. So it's the idea of, like, you tell it what you want to do. You don't worry about where it happens or how even it gets to that state. It's this idea that you submit desired state to a system, right? So you say to a system, I want to run the following things. And I don't care about how they run. I just want you to look after that for me, please. That's the job of these orchestration frameworks, is to hide the complexity of all the machines sat behind the big computer, and just to present with you a resource of CPU, RAM, networking, and storage. So much like the composer of the music is not worrying about what time the orchestra turns up or where they sit in the room, the composer is providing desired state in the form of the sheet music, and it's the conductor's job, the orchestration framework's job, to take that sheet music and enforce it on the orchestra to play, and that's how it actually comes together. So for the composer, you don't have to worry about all of those complexities. There's the developer. For the conductor, there's the orchestration framework. I'll stop killing that metaphor now, I promise. But here really we're talking about, the common abstraction across the three tools we're going to look at today is treat your data center as one big computer, and it reduces all of the complexity of trying to think about more than one machine. So I love this picture. It's like, if only data centers were actually like that, probably they wouldn't be very fast. Right, move on. So we're going to talk about three main orchestration frameworks today. But before we do, because I'm going to go into these three, there are others, right? So a challenge to the audience, like, who can name another orchestration framework that's not on the screen right now? Somebody take the bold step of speaking. Nobody will bite you, I promise. I mean, I'm not going to just give you the answer. George, another framework? No? Okay. Somebody, come on. No? Okay, well, I can fill in a couple of others. Amazon ECS, for example, like the Elastic Container Service. It's an orchestration framework. You tell it what you want to run. It turns around to machines and runs containers on those machines for you. There's HashiCorp Nomad, which is like a fairly new player in this space. It's much like these three. There's Cloud Foundry, which is a much older one. There's some others as well, which I've probably forgotten to mention, DrSwarm. These aren't the exclusive three. It's just probably the most popular three, and it's the ones we're going to take a look at today. So, Swarm. Is everybody comfortable with how Docker works? As in, it presents a REST API and everything? Raise of hands, otherwise I'll tell you very quickly. Yeah, okay, great. Good, nice. Your arms do work. So Swarm is effectively like a proxy to a whole number of back-end Docker servers, right? So you have a Docker CLI, so you can say Docker info or Docker PS or Docker run. It's a command line tool, but what it does is it sends a JSON packet over HTTP to the Docker server. So it's not invoking the container immediately on the command line. It's sending a packet over the network to the Docker server. And what that means you can do is have like a proxy in between the CLI and the server. And that's what DrSwarm is. So if you take a single Docker server and it's just on one machine, there's no clustering or orchestration going on, it's just one Docker instance, and you say Docker run, it's sending a JSON packet to the Docker engine running on that computer. And the engine will do what you've asked. I run a container or list what's running. If you put a proxy in between that CLI and that server, then that proxy could effectively be choosing one of 10 backend Docker servers to send that request to. So DrSwarm is a neat trick because it basically says, I'm going to present a standard Docker server. So all intents and purposes, it looks like it's just a single Docker instance. But behind there's 10, 100. At DockerCon in Barcelona, we saw a demo of 1,000 nodes sat behind a DrSwarm. But to all intents and purposes, the client that's using the DrSwarm couldn't really tell the difference between it being 1,000 servers or just one, because it presents the standard Docker the standard Docker API, with some slight differences. I mean, it allows you to see what computers there are on the network and some additional things. But the key thing is anything that speaks the Docker API can speak to DrSwarm. So it's like a compatibility layer for scaling out your Docker cluster. It's made by the core Docker engineers. So I think it was maybe the first DockerCon when a demo of Swarm popped up, and Anand Prasad, who composed, did the demo at DockerCon, the #1 in San Francisco. And he was basically like, oh, look, I've got this really cool thing where you connect to a Docker server normally, but actually it's 10 Docker servers behind. And that was where Swarm became, the beginnings of an orchestration framework. But it's Docker's own solution because they want to run this whole space, it seems. They're not content with just being the container runtime. They want to run the entire data center. This is their solution to orchestrating your data center, DrSwarm. It's written in Go, as Docker is, so it's kind of like an extension of the Docker project, if you think of it in that way. Like I've said, it uses the standard Docker CLI and the Docker REST API. It's just kind of a multiplexing proxy, right? So it's like, I speak to one thing, but it decides which backend server it speaks to at the back, right? So it uses console. If anybody happy with console, it's like a distributed state system. It uses Raft underneath, so it's kind of distributed consensus, basically. So you need this because if you have a single master and then that goes away, then nothing works. So the idea would be to have several swarm masters, and by swarm master I mean the thing that the Docker CLI connects to then be proxied to the correct server on the back. If you only have a single master, then it's fairly brittle. You don't have HA. You need something like console to distribute the current state of the cluster to the other masters, and such that there's no single master. All of the masters always have the same view of the cluster, and now one of them can blow up, and you still have a functioning swarm cluster. So this is this idea of distributed consensus, and it goes through all three tools. All three of them have a distributed consensus tool at the core of them, such that they can provide HA master functionality. And if one of your Docker Swarm servers goes away, the other takes over, and it always has the same state as the other masters at any given time. Kubernetes. So for the last 12, 13 years, Google have had a tool internally called Borg. Sort of sounds as scary as Google's size is becoming, I think. It's like the tool that manages their huge scale, like hundreds of thousands of machines, and 2 billion containers a week, I think, is Google's numbers. Do you know? A third, just under a third the population of the planet. Every week they're starting a container. So the scale is mind-boggling. I can't even begin to think how that works. But hey, they've told us because they wrote the Borg paper. And this is great. So the Borg paper is a great read. It really, really is worth reading that paper, even if you're not really intending to get into these what What is Borg? It's a tool that developers say, I want you to run this stuff. And much like we've seen before, it's like treating the whole data center as one big computer. Borg will turn around and schedule the work onto a machine, make sure everything is functioning, move work around. Everything is run in a container, not a Docker container in the world of Borg, but we'll move to Kubernetes in a sec. It's kind of native Linux containers with a Google wrapper. Kubernetes is effectively an open source version of the Borg way of doing things, right? So Borg will never get our hands on it. It's a private Google tool. It's what runs their data centers. Tim Hockin and Brendan Burns, the sort of two Google engineers that kind of thought, oh, this new Docker thing is pretty cool, and Go is a nice language to program in. Why don't we write Borg in Go for Docker? This is Kubernetes. And it's fantastic because as us mere mortal developers now, we can take on some Google technology and basically run our tiny little data centers and our tiny little operations in the same way they run their large ones. And when we take over the world, then we can scale up to Google scale. It's also written in Go. As I said, I think Borg is C++, and you know the Kubernetes engineers thought, hey, we have this wonderful new language called Go that deals with concurrency, so we'll write Kubernetes in Go. I mean, Docker is also written in Go. It seems like most container tools these days are written in Go. You use a Cubectl tool. Right? So whereas Swarm is effectively you use the normal Docker CLI tool to get things scheduled onto the cluster, Kubernetes has its own CLI tool. It's called Cubectl. There's a whole bunch of different concepts in Kubernetes. I won't go into, this isn't like a deep dive into how the three things work, but there's pods, which is effectively a collection of containers, like 2 or 3 containers. The good example is a Minecraft server and a Minecraft analysis process that looks at the map continuously. Now, these two things need to be scheduled onto the same machine because they share a volume. So one of those containers is reading data from the disk that's being generated by the other container. So really, you kind of need to say, I don't want this analysis container to run on a different machine to the Minecraft server. They have to go together. So Kubernetes has this idea of a pod, which is effectively an atomic unit of containers. If one of them stops or one of them's moved, all the rest of the things in the pod are moved as well. So there's its kind of core unit of operation for Kubernetes is you describe pods. You also control replication controllers, which is a way of saying, I want 5 copies of this pod running in my cluster at any one time. And that's Kubernetes' way of doing monitoring and failover, because it's saying, oh, look, this pod, this Minecraft pod just had a problem. How many are there running right now? There's 4. Oh, the replication controller says I should have 5, so let's start another pod on another machine. So it's kind of going down a layer now. How can we actually do failover and monitoring? Replication controllers is the tool that Kubernetes uses. etcd is used for cluster state in Kubernetes. etcd is an equivalent to console in that it's an implementation of the raft algorithm, which is known as a simpler version of Paxos. All of these words fairly comfortable to you? I mean, yeah, a little couple of nods. All right, a real quick dive. Like, for us to all agree on a value, so imagine I said, who's the best football team in the world? Well, Arsenal, obviously. I'm not actually going to get you to try and agree to that, but like we'd have to reach some form of consensus around the room before we would all agree that now somebody from outside the room could ask us that question and we'd give the answer. So this is this idea of consensus. And etcd and console both use the raft algorithm, which is, again, it's a paper. If you go and search for raft paper, it describes how to architect a system such that we could all come to a consensus value. And then if one of us decides to go home, somebody else could take over, and we still have a consensus. So it's kind of a high availability trick for running, keeping consensus of the cluster state across more than one machine. So it's an equivalent to console, which is what we saw Swarm uses. Kubernetes uses etcd. I'm not sure if there's much difference between the two tools when you just look at distributing state across a cluster. Next one, Mesos and Marathon. So this is incubated by Twitter. It was written by a student at Berkeley, just as a kind of like, hey, well, let me be clear. Mesos was written by a student at Berkeley. And these are in the days of the Twitter fail whale. I don't know if anybody remembers this, but, you know, hey, I want to use Twitter. Oh, sorry, we're not working. Continuously, it was an ongoing saga, right? So Twitter really needed to do something about their architecture. They kind of noticed this tool, Mesos, and thought, oh, this could start to solve it for us. So a really good pedigree for Mesos is it runs Twitter's infrastructure. And it's what's kind of helped them go from Ruby app that always fails to, I mean, I can't remember the last time Twitter didn't work, okay, a couple of months ago, but it's fairly stable compared to how it used to be, right? It's Scala now, that's right. So I think the story I heard is like, yeah, we have this massively successful social application, here's Twitter, but our software is really shit, so we need to get some people in to do this properly. So Mesos and Scala was the answer to that. And Mesos, what is Mesos? It's like a hardware scheduler, right? So there's a Mesos master and a Mesos slave running on every computer in the data center. So if you have 1,000 machines, all 1,000 of them are continuously reporting to the master, I have 4 CPUs and 10 gigs of RAM free that aren't doing anything. So it's a very low-level thing, Mesos. It doesn't really have an opinion about how you're going to use those resources. It just says, hey, I've got some compute resources if you want to use them. Marathon is like a layer on top of Mesos. And we'll look at frameworks in a bit, but frameworks are effectively like an opinionated way to consume those resources. This is how Mesos is architected. So this is why you continuously hear about Mesos and Marathon as a pair. They are two very separate projects. It's just one is a layer on top of the other. So Mesos is like the kernel of the data center. It kind of looks after the access to the hardware of the data center. And Marathon is like the init system of the data center. It looks after what should always be running, and it uses Mesos's resource offers to decide which computer to run stuff on. So there's a basic sort of underneath idea of Mesos. It's written in C++, which is different to the other two tools, but hey, I mean, I'm not sure if any is better. I mean, let's not have a language argument, rabbit hole. Right, so how do you interact with this? You use the REST API. There are CLI tools for Marathon, much like kubectl is the CLI tool for Kubernetes, and the Docker CLI is the CLI tool for Docker. Mainly, though, you interact with the REST API for Marathon, and you're basically telling it, hey, I want to run the following collection of containers in the same way that with Kubernetes, you're saying, I want to run the following pods, and it will use the Mesos resource offers to schedule these containers onto the most appropriate machine. It uses Paxos for its distributed consensus. So this is why we've been talking about, we need to maintain consensus, because otherwise we can't have a highly available Mesos and Marathon. Paxos is an older consensus algorithm to Raft. It's known as the complicated one. In fact, why Raft existed, and this is like the tagline for Raft, is Raft, a simple Paxos implementation. So Paxos is notorious for being quite complicated. Here's the kind of DNA of the three tools. I've kind of rambled on about some various little bits and pieces. How are we going to actually compare these things, though? Now, I don't know if this is going to work. We're going to try it. And this is what my sister was helping me with last night, is to make some top trumps cards. So we're going to play ease of installation first. Does everyone know top trumps? I'm assuming that this metaphor. Okay, good. Right. So documentation. I mean, the documentation for Swarm is excellent. I mean, part of it is, if we go down to the bottom thing, moving parts and configuration, these aren't that hard compared to the other two systems. So it's kind of unfair to say, hey, the documentation is excellent, because it's actually, there's not a huge amount to the documentation, because it's a simple thing compared to the other two. But in my experience, it's taken 5 minutes to set up Swarm. It's never really been a painful experience. The documentation guides you through the process in a very clear way. It's the simplest of tools to get your hands on out of the three. Kubernetes, I was talking with Matt, who works for JetStack. And by the way, if you ever need to know anything about Kubernetes, like, these guys are the experts. So if Kubernetes gets your attention, then Matt, Bates over there from JetStack is the guy to speak to. I was asking him yesterday, what do you think about the Kubernetes documentation? And we're like, should I put a low score or a medium score? And we're like, well, it's really good. It's just like they've admitted themselves that the documentation could do with a lot more work. So I think I would have put like a medium score on the Kubernetes documentation. There's lots of it. It's just like, it's confusing at times, right? And there's a lot of concepts. Let's move to the moving parts side of things. There's a lot to Kubernetes. There's like the API controller and the scheduler and all sorts of different parts you have to understand before you can configure and set up a Kubernetes cluster. Mesos and Marathon kind of sits in the middle. The documentation side of it is reasonable. Every time I've set up a Mesos and Marathon cluster, it's been fairly trivial. I mean, it's not nearly as simple as Swarm because there's more moving parts. So the configuration of the three tools, again, Swarm doesn't take much configuration. Each slave, if you call that, not the master servers, the 100 Docker servers you have in the back, really all you're configuring is, hey, here are the master servers to speak to. Because there's not much more to it other than I am a Docker server and I'll be proxied to from the Swarm master. Configuration of Kubernetes is, medium is more to it, therefore it's harder. But there's not much to either of Mesos and Marathon in terms of how you configure them. It's mainly a case of saying, for each slave, for each sort of node in the cluster as opposed to the controllers, you're basically saying, here are where the masters are, and communicate with them. It gets slightly harder if you're talking in TLS, which we'll go to in a bit. But fundamentally, Swarm is the easiest of the things in terms of configuring, and Kubernetes and Mesos are about medium. I mean, none of them are that painful. And obviously, for their UX experience, it's quite important that they've made it not that painful. So otherwise, they wouldn't have huge amounts of users. Moving parts, I mean, Swarm doesn't have that many. It has the Swarm master and the Swarm agent on each node that you're proxying to. There's a console server thrown in for effect if you want HA. Kubernetes has quite a large number of moving parts. For a beginner, when I first sat down with it, it was overwhelming. I was like, I can't remember what the controller is versus the scheduler versus the API part. I don't know what these things are. So there's a lot of bits and pieces to Kubernetes. It's kind of like it's composed out of lots of bits, is the way that they've architected that system. With Mesos and Marathon, less so. There's a Paxos server, the Mesos master, and the Mesos slave. So it's more than Swarm, but less than Kubernetes in terms of moving parts and therefore how complicated it is. So a kind of quick summary of how easy they are to get going. I'm famous for going over time, so I'm going to check the clock, and I think I'm doing okay. Right, compatibility. What do I mean here? It's like, how many different things can you run on these systems? So Swarm scores quite lowly here, because Docker are trying to take over the world with their Docker thing. So guess what? It only runs Docker containers. So it will not run anything other than a Docker container. So let's be clear about that. If you're looking at a workload that might involve anything other than Docker containers, you can't use Swarm. Well, you could, but you could only use Swarm for the Docker container parts of it. Kubernetes has quite decent container support. It's adopted the idea that it shouldn't have a strong opinion about which container runtime it should work with. It started off supporting Docker, but now also supports Rocket containers, and with all of the new containerizers that are coming into the fray, Kubernetes is very much set up with the way that it works, a modular containerizer code base that it's very set up to support anything new that crops up. I can't remember the one we were talking about last night, but I'll get to that at the end. Non-container support, Kubernetes doesn't really do non-container support. It only runs containers, right? So it's very much a new tool. It's focused on containers, unlike Mesos and Marathon, which can run anything. So Mesos and Marathon has the concept of containerizers. You can run Docker containers. There's another thing called the Mesos containerizer, which is just a hook into the Linux syscalls to start a container. But crucially, you can run any process you want. So you could say to Mesos and Marathon, I want to run time as a process, and it'll just print the time out. That's fine. Anything that can run on your Linux machine, you can instruct Mesos and Marathon to run. And so it scores very highly for non-container support. And that's quite important, because if what you need is a mix and match of containers and non-containers, Mesos and Marathon will do that for you. Extensibility, like how can I take these tools and add stuff to them, because not everything does things in the way that I want. Well, Swarm, the number of plugins, there's kind of two main areas. There's three main areas. There's storage, there's networking, and there's scheduling. And because it's quite a new tool, there's not a huge number of them. For storage, with Cluster HQ, we worked with Docker quite a lot last year to get the volume plugin mechanism into Docker itself. Being storage people, that was very close to our hearts. And people like we've worked with Docker to get the networking plugins plugged into Docker itself. So it was only really in the last 9 months that plugins have even existed in Docker. So for that reason, there's not a huge number of them. How to write them, though, is really simple. And we'd like to take a bit of credit for that, because we were part of the whole process. No, let's not use HTTP2 or SSH. Let's just use JSON over HTTP. It's the simplest thing. So to write a plugin for Docker Swarm and Docker itself, you can write in any language, because it's contacted over HTTP. So you could write a Ruby process that is a Docker volume plugin. You don't have to compile the code as Go and recompile Docker to write a plugin. I'm going to hurry up now. So with Kubernetes, it's somewhat harder to author a plugin. You have to write it in Go. You have to merge it into the Kubernetes code base. It's not as easy as Swarm, because you can't write in any language. You have to kind of follow the Kubernetes opinions of, like for example, a volume plugin is very much, given an exact data structure. You have to put the code in the exact folder. You have to recompile some Go. It's harder. Mesos has this concept of frameworks. Marathon is a framework. There's lots of other frameworks. There's Chronos, which is like a cron system that uses the Mesos resource offers to schedule work at certain times. But it's quite hard to write a Mesos plugin. Well, a Mesos framework is what I'm calling a plugin there. It's notoriously hard, because there's lots of moving parts, and it's harder than a Kubernetes plugin, for example. So in terms of ease of authoring, Swarm is much easier. Kubernetes somewhere in the middle. Mesos is hard. But you could do a reverse for the power, because with Mesos you can write literally anything you want that consumes a compute resource. Whereas with Docker, it's very much like, start a volume, here's the name of it, and all you get to hook into is that moment. So Mesos is more powerful, but much harder. Storage, right. So for Docker Swarm, there's a number of storage plugins. Flocker exists as a storage plugin, which is a tool Cluster HQ have made. There's a couple of other storage plugins, like there's a Ceph plugin, I think, in the works. And but again, because it's quite new, there's not the biggest range of storage plugins. People are busy writing them, but it's still quite early days. With Kubernetes, there's excellent support for a whole range of different storage plugins. And there's also a Flocker plugin for Kubernetes. This is my mandatory pitch. But there's also a native NFS driver. There's a native Ceph driver. There's a native AWS driver. So if you're looking at using Kubernetes and you're thinking, how do I save my state in my cluster, take a look at the list of Kubernetes supported storage drivers, because it's really, really good. Mesos and Marathon, much less so. They've only just got their heads around the idea we need to get state involved in the cluster, and we need to natively support that within Mesos and Marathon. There's also a Flocker framework for Mesos and Marathon, end of plugs for Flocker. How do they deal with HA volumes? Well, Swarm doesn't really do HA volumes. It doesn't really understand scheduling if something fails, and it will do. I mean, that's very much the path they're on. Kubernetes is excellent at HA volumes, as is Mesos and Marathon, because really that's the DNA of these tools, is to say, hey, I'm going to be monitoring all of these processes. If something fails, I'm going to move it around. In the process of moving something around, I'm going to reattach the storage to the new location. So both tools are very good at migrating a database and its state between one place and another place if it fails. So if this is what's important to you, one of those two as opposed to Swarm. Networking. Service discovery in Swarm is really good with their new Docker 1.10 networking layer, where they've built in Docker links across more than one machine. So it's literally the case of you can contact one of your services using the host name, and it will automatically resolve to wherever that process is on the cluster. So it's very, very good at service discovery, as is Kubernetes. Kubernetes has this concept of services, which is like an abstraction for, hey, I've got my 10 news processes running, and I just want to use a host name to get to one of those, and Kubernetes, using some IP tables trickery, will automatically route to one of those services, and you don't have to think, is it alive or where is it? So both those tools are really good at service discovery. Mesos and Marathon less so. It does this kind of HA proxy trick where it knows where stuff is and it rewrites HA proxy rules, but not instantaneously, and it's slightly more clunky than the other tools. Vendor support for Swarm and Kubernetes. Let's go through the three main networking layers: Weave, Calico, and what used to be Socket Plane until Docker bought them, which is now what we know as Docker native networking. So if you think about overlay networking and how you get traffic from one place to another where everything's moving around, Docker Swarm and Kubernetes both have support for most of the main tools, which is great. Mesos and Marathon less so, because they, as I said, they're kind of using this HA proxy rewrite the rules trick. They don't have native support for things like Weave, but you can use them. But it's just you have to plug it in yourself. Right, I really must hurry up. We might skip a couple. So scaling, capacity for Docker Swarm, we saw 1,000 nodes at DockerCon in Barcelona. Kubernetes is very adept at running more than, in the thousands of machines. Mesos scores very highly here. We're talking hundreds of thousands of machines if you need to get there. If you imagine Twitter's scale, that's where they are. Failover, as I've said, Swarm doesn't really do it. Kubernetes is excellent at failover, as is Mesos and Marathon. So the more that you scale, the more likely you are to fail, and you need your orchestration tool to be able to deal with these things. How difficult are these things? Well, Swarm is fairly simple because it's a case of adding a new node and pointing it at the master. Kubernetes and Marathon is neither simple nor difficult. It's a case of adding a new node, and it's the same as the configuration. How hard are they to configure? When you add a new node, you need to configure where it is, and where is the master, and configure some other things. It's slightly harder than Swarm, is the point I'm laboring there. What we're going to do is quickly go, all three have TLS support. Swarm doesn't really understand users. Kubernetes has excellent user support because it has a thing called namespaces, which lets you run entire stacks separately from other stacks, even though they're on the same Kubernetes cluster. Mesos and Marathon kind of has the idea of users, but doesn't have namespaces. So I think Kubernetes wins that one. Kubernetes has far more stars, far more contributors than the other two tools. The other two are about the same. In terms of popularity and exposure, Docker has got a great marketing team, so everybody gets to hear about Swarm. But really, Kubernetes wins this because of stars and contributors. I'm going to go through this now. I'm going to skip Solidity. Basically, Mesos and Marathon has been around for ages, like 5 years. It runs Twitter. Every time you use Siri, you're using a Mesos cluster. It's kind of proven in production. The other two aren't that old, right? 2 years. There's beginning now people using Kubernetes in production, but we're not quite there yet. So Mesos, hands down, wins the Solidity round. And I think I've managed to talk my way out of time. So we're now going to hit the podium in one quick list. And then we can ask some questions. So really, there's a summary. These are arbitrary values, right? I've kind of looked at my own experience here. It's by no means a final dictation on which tool you should use. But as a summary down the list, here is where we've gone, which tool is best at which area. So I'm going to just quickly skip to the last and then go back to that last slide. I just want to point out two things. My sister helped me tremendously with the Top Trumps cards last night. I'm like, shit, I have a thing tomorrow and I've not even started the slide. She goes, well, I could make you Top Trumps cards. So thank you to Ivy, my sister. And the second thing is this whole thing is running in Docker because I'm using Reveal.js. But I'm going to leap back to that page and quickly say if anybody has any questions before I really run out of time. No questions?
What's the difference between Mesos and Marathon and Mesosphere? And what happened to Weave scope?
Good question. Two questions. So Mesos and Marathon and Mesosphere. Mesosphere is a company. Mesosphere created Marathon. Mesos itself was around before Mesosphere, right? So Mesos itself came out of Twitter. As I said, it runs their infrastructure. That's telling me what I already knew. And Marathon is like a Mesos framework set on top of Mesos. Mesosphere is a company that's commercializing the entire package of Mesos, Marathon, and Chronos into something called DCOS, which is Data Center Operating System, which is their commercial offering. So, and it's a confusing thing. Think of Mesosphere as a company. And Mesos is the underlying hardware layer, and Marathon is the scheduling layer on top of Mesos. Weavescope is still around. They're working on it really hard. Weavescope, for anybody who doesn't know, Weave is an overlay network, so it's a dynamically routing networking tool. Weavescope is a thing that uses PCAP to analyze network traffic around your cluster and kind of visualize all your containers in a lovely React.js GUI. But I think the answer is it's alive and well. Have you heard something to say it's not around?
I know it was a way to visualize the cluster itself.
Yeah, it's an excellent tool, Weavescope. It's sort of, you don't need to tell it anything about your cluster. It just knows where the traffic is heading because it's analyzing all the traffic using PCAP. And as I said, Weave is a tool that's a kind of... Weave, by the way, works with all three of those tools very much as a Docker plugin and a Kubernetes plugin. I think I'm out of time now, so I'm going to leave it there and say thank you very much for having me. And